Thank you for staying so late. And today we're excited today to present on this OC3 2025 conference, the next step of confidential compute by Intel TDX, the Intel TDX Connect, which bridges the CPU connectivity with trusted devices. And today we're going to speak about the vision and goals of Intel TDX Connect. We're going to talk about the TDISP industry standard and explain how it bridges the TE between the CPU and the PCIe devices. And we will show you the overview of the architectural framework, along with full software, end-to-end software lifecycle and attestation. And finally, we'd like to encourage you to get involved in the confidential I/O ecosystem. By the way, can you see my screen? Okay.
Yes, we can see your screen and now in full mode. Yeah, thank you.
Oh, okay. Sorry. Okay. So first, let's talk about TDX Connect goals and what is Intel TDX Connect. So Intel TDX Connect is based on PCIe standard, which provide heterogeneous CPU and accelerator confidential computing standard. Let's start with the left-hand side. So this slide, you can see the differences between trusted I/O with base Intel TDX Connect. And on the right-hand side, you see the TI/O with Intel TDX Connect. So let's start with the baseline. So with the baseline, since devices and the CPU cannot access private memory of each other, we have to use an encrypted bounce buffer for the data movement between the device and the CPU and vice versa. This is an inefficient data movement, of course, because it requires the overhead of encrypting the data before copying it out, and then copying it in and decrypting it and authenticating it again. It also means that for this solution, because the device is not directly in the TCB and there is no standard, this solution relies on proprietary or some infrastructure changes which are not standard. On the right-hand side, we see TDX Connect, which is based on PCIe TDISP standard and SPDM from the MTF. Basically, this unlocks the connection using device and CPU direct access to private memory for both MMIO and DMA, relying on PCI Express hardware accelerated link encryption, which is more efficient and closer to real data movement speeds with PCIe fabric. And it uses standard as its baseline, which defines the common way for how to connect TI/O devices with confidential compute CPU trusted VMs. So the benefit is, of course, you gain broader adoption and compatibility. You don't need to rely on a standard solution, and instead of concentrating on the hassle of protecting the data, building all the framework and all the pieces, you just the programmers can just focus on the workload itself, relying on PCI Express data movement and this layer of confidential standards. So the next question is, how do we add the I/O stack to the existing Intel TDX framework? How do we add the I/O stack connectivity and security with the host-based VM isolation of TDX? So the first component or ingredient in this framework is going to be the TDX module, or in the language of the standard, it is called the Trusted Security Manager on the host side. The goal of TDX module is to ensure the isolation between the trusted VMs or the TDs on the host platform, which is now extended to orchestrate and to secure the I/O connection, starting with establishing secure SPDM connection with the device, and then establishing the IDE link protection between the device for securing the data movement using PCI Express over the link. It also extended to support secure management of device binding to TDs or to trusted VMs using the TDISP protocol. And finally, it uses secure management of MMIO mapping and DMA mapping to ensure the isolation of devices between TVMs and ensuring that the MMIO inside the device is isolated between different TVMs or TDs, and to ensure that the device is assigned to, which is assigned and accepted to the TCB of the TD, can only access the TD assets and nothing more than that. The next ingredient is the hardware, which ensures that we can generate private MMIO transactions and send them securely to the device using the IDE encrypted link. The third component is the extensions of our VTD with trusted IMMU. The trusted IMMU extensions provide trusted DMA remapping structures and tables, which are explicitly controlled by the TDX module. And the TDX module controls them to ensure the isolation, again, that the DMA and device peer-to-peer can only access the TCB of the TDs they're assigned to. The fourth component, of course, is the link itself. So the link itself needs to be encrypted and protected. And the link protection is established according to PCIe IDE specification. The TDX module orchestrates the IDE configuration and ensuring that the link is protected and secure before connecting devices to TDs. The last component on the right-hand side is the TDISP compatible device, which supports the standard SPDM secure session establishment and attestation reporting, supports the same IDE protection over the link, and it has the device security manager, which is the device firmware, which enforces the TE isolation within the devices and enforces the lifecycle management of the device assignment to TE. So before we look into the lifecycle, I just wanted to give you a short recap about TDISP. So the goal of TDISP is to establish the trust between the host trusted VM and the device. This establishment is based on SPDM attestation and an SPDM secure session, which is used as the secure transport for additional protocols, like the protocol that established the secure connection, the PCIe IDE connection, and also the protocols that manage the T device interfaces state machine. So the second component is, of course, the secure link, which we talked on the previous slide, which is based on PCIe IDE. This link protection is an end-to-end link, which also protect the link from untrusted switches on the PCIe fabric. The third responsibility is to define the secure binding process between the TVM and the TDI, the device interface TE on the device. The security model of this connection is must ensure that the TVM, the TD inside the host, is able to first observe that device is locked and then request the device attestation information and confirm the device configuration is done in the way that TD accept, and then the TD can independently accept the TDI into its TCB. And the last requirement from the TDISP protocol is the definition of how the device should protect the data and the state of the confidential workload running inside the device. And this is just to zoom into the state machine. So the state machine is managed by the device security manager per device interface, which is assignable to a host TEVM. This state machine defines two main states. The first state is the initial state when the device goes out of reset. This state means that the device is not in confidential mode. It doesn't have any secret, and it may be configured and prepared for becoming a confidential device. The next state is called config locked. This represents the state of the configuration of the device. In this state, the device still does not have any secrets and any confidential data, but it is required to ensure that the configuration is not changed because it needs to report its configuration and attestation at this point and presented to the TVM running on the host. If the device senses that configuration is changed, then the device needs to move into the error state, which is a trap state. The next state is once in configure locked, then the device can get messages from the TVM. The TVM needs to get the device measurements and attestation, and also the configuration report. Once the TVM gets the measurements and the TDI report, it can independently decide whether it is willing to extend its TCB and accept the device into its TE. Once the TVM decides the device and its configuration are acceptable and trustworthy, then it can issue a request to move the device into its run state. This is the operational state of the device. This is where the device is accepting MMIO accesses, which are marked as trusted with PCI IDE TBIT, and also sends trusted DMA requests to the host, which can access the TVM private memory. And again, all these accesses are protected with the IDE link protection and are marked with a TBIT. And in this state, the TDI must protect all the TD workload data and state. Finally, if there is any security violation, the DSM is responsible to transition the device to the error state. And again, this is a trap state, which may still have secrets. And the only way to get from this state back to the original state, the unconfig locked, is if the device can confirm that all the secrets and all the private state has been cleaned from the device. Let's move to the next part from Shalini now.
Hello everyone, thanks Ari. So I'm going to walk you through the TDX Connect software lifecycle. The main motivation behind this lifecycle is to ensure that a trusted device interface is securely binded and unbinded from a trust domain or a confidential VM. And it is ensured that only the trusted devices which are verified through the process of attestation are added to the trust boundary of the confidential VM and given access to its private memory and allowed secure execution in a confidential computing environment. So this life cycle can be divided into 4 key flows. The first flow is depicted in steps 1 to 7, and this is the TD requested bind flow. The second flow is depicted in step A, and this is the TD requested unbind flow. The third flow is depicted in step B, and it is device removal flow. And the fourth flow is depicted through step C, and it is the PFFLR flow. So let me talk about the TD requested bind flow. In the TD requested bind flow, it is the TD that requests the trusted security manager to transition the device from a non-CC mode to a CC mode. This is facilitated through the VMM and through the TSM, which is the trusted security manager. The process begins with VMM discovering the TDISP capability in the device and then setting up an SPDM session. So the SPDM session is established between the trusted security manager and the host and the DSM and the device. After the SPDM session is established, all the communication related to ID key programming and TDISP state change occurs over this SPDM session. So the next step after the SPDM session establishment is the IDE key programming step. The VMM enables the IDE in the root port as well as in the device endpoint. It programs the necessary keys required to protect the confidentiality and integrity of the PCI fabric from the untrusted PCI fabric. After these two steps, the device is assigned to the guest, and the guest then enumerates the TDIO capability inside the device and request bind. At this point, the guest is asking the VMM to transition the device from a non-CC mode to a CC mode. The VMM sends this request to the TSM, which then executes a set of TDISP commands to transition the TDI into a config logged state, and also generates an interface report, which is provided to the guest. After this step, the next step is the attestation. The guest TD collects the measurement from the device. The guest TD can either reuse the measurement that was collected during the SPDM session setup, but in case it wants to collect fresh measurements, for example, if a firmware update occurred after the SPDM session was established, it can recollect this measurement and provide this measurement and certificates to a verifier for verification of the evidence. After that, the guest validates the MMIO based on the interface report it received during the bind, and validates the MMIO and also validates the DMA. After the acceptance process is complete, the guest TD transitions the device into a run state. The guest TD requests the TSM to send the TDISP commands to the device to transition into the run state. After these steps, the device is securely binded to the guest and is ready for secure execution from its private memory. This specific life cycle describes a flow where the TD initiates the bind process. We think that this flow is more relevant in the use cases that are involved. For instance, one of the use cases is the direct device assignment, where the device is directly assigned to the guest. And in this case, the guest driver may want to configure the device, update its firmware, and then want to transition the device into a config logged and subsequently to the run state. So in that case, this kind of flow is more suitable. There is another scenario where the guest may want to perform an error recovery on the device through a VFFLR. So in that case as well, since for a TDISP device, VFFLR will transition the device to an error state, it is required that the device is first unbound from the guest and then rebound for successful completion of error recovery. So this basically explains the TD initiated bind flow. Let me go to the next flow, which is the TD requested unbind flow. When a device, when a trusted device has an error, or if the guest wants to unbind the device, it will request the VMM to unbind it. The VMM uses the Trusted Security Manager to send the TDISP commands to transition the device to unlocked state. And also it unmaps the private DMA and MIO that mapped the device to the private memory of the guest. After this process is complete, then the device is unbound from the guest and is ready for rebind, which is shown in step A here. Another flow which is important is the device removal flow. In case VMM wants to remove the device from the guest, it will send a device removal request to the guest, and on receiving the device removal request, the guest stops accessing the TDI and prepares for the TDI to be removed from the guest. After this, the VMM takes over the TDI and unbinds the TDI, transitioning it back to the unlocked state. And now the device is ready for reassignment to the same guest or to another guest. The last one I'm going to talk about is the PFFLR flow. In case the host VMM wants to perform a PFFLR on a device which is owned by the guest, the VMM sends a PFLR request to the guest. On receiving the PFLR request, the guest is going to stop accessing the TDI and prepare itself for PFFLR. The host VMM will unbind all the TDIs inside the device, and after that, it is going to tear down the IDE and then perform the reset. The reset will transition the IDE to insecure state, and the IDE needs to be reset up, and new keys need to be reprogrammed before the device is ready for reassignment to another guest or to the same guest. So this life cycle basically ensures that it integrates the aspect of secure device attestation using TDX Connect, TDISP, and also allows mapping of private MMIO and DMA to the guest. And it allows secure tear down sequences, so the devices can be securely removed from the guest and reassigned to another trusted VM or another TD.
Should we move to the attestation flow?
Yeah, let's go to the next flow. Yeah, so this slide explains the device attestation flow. So the device attestation flow begins with the VMM requesting SPDM session setup. During the SPDM sessions setup, the device transmits the certificates and measurement, which the digest of those certificate and measurement are collected inside the TDX module. And the certificate and measurement are provided to the VMM to be stored, so that the later, when TD wants to perform the bind or it wants to perform the remote attestation, the TD can collect it directly from the VMM. After the SPDM connection is established and certificate and measurement are exchanged, the guest and the device is assigned to the guest requests bind. As a result of bind, the TDI transitions to locked state, and it generates a TDIS report, which has information about the private MMIO inside the device. The TDX module records a digest of this interface report to be used later by the TD when the TD requests it. Finally, the TD requests these attestation objects, which includes the device attestation info and also the TDIS report. It asks the TDX module to validate the authenticity of these objects. The TDX module checks the previously stored digest of attestation object and as well as of the TDIS report and verifies the authenticity. It prevents tampering of these objects which are stored inside the VMM from the VMM. And in the final step, if the TD wants to recollect the measurement, for example, if the measurement was collected at the time of SPDM setup is stale because a firmware update happened after the SPDM session was set up, then the guest can recollect the measurement through the TDX module. In this case, the guest provides a nonce to ensure the freshness of collection, and the TDX module recollects the measurement and provides the recollected measurement to the guest. Using this recollected measurement and recollected certificates, guests can perform device attestation. So this flow basically ensures that the attestation objects and interface reports stored inside the VMM are protected from tampering, because TDX module stores the digest of these attestation object and interface report inside the TDX module. It also provides a capability for guests to recollect the measurement in case of a firmware update after the SPDM session was established, and it allows basically a mechanism to provide information for secure device attestation. Thank you. You can take the control back, Ariya.
Thank you. So this is the end of our quick overview. If you'd like to get involved, so there are a lot of ways to influence and learn. You can tap into TDX today, starting your build, measure, learn process with available deployment. We have available deployment of TDX. even with devices, but with proprietary mechanism, for example, the NVIDIA H100. But this is a very useful way for you if you want to start deployment and learning, because the next generations, right, are expected to give you more performance and more hassle-free integration with an ecosystem that involves standards. It's also important to know that this ecosystem requires heavy lifting from Linux upstreaming. So there is currently a community for the confidential compute and TDISP, which is under the Linux Coco mailing list and community. So you can also join this community and follow up the mailing list and get notification for the most recent changes of upstreaming. You can also get involved joining the PCI SIG and DMTF standards. These standards are constantly improving and enhancing to support more use cases and scenarios and solve more problems. It's important to note that in order to use TDX Connect, you need a TDX Connect supported platform, which the first one is going to be Xeon 6 on GNR platform. You need to use an enabled PCIe device. And you need to use an enabled OS or hypervisor. We started the ecosystem enabling with our major CSPs collaboration. The Linux upstreaming, as I said, is underway. And we have some collaborations with industry leadership of TDISP devices, for example, NVIDIA Blackwell. And yeah, so I think we have little time for questions.